Now we are on subtopic 37.4, the diffraction grating. The diffraction grating is actually a useful device for analyzing light sources. Consists of large number of equal spaced parallel slits like this. Right? A transmission grating can be made by cutting parallel groove on a glass plate with a precision ruling machine. The space between the groove are transparent to the light and hence act as separate slits. The reflection grating, second type of the grating, can be made by cutting parallel groove on the surface of a reflective material. The reflection of the lights from the spaces between groove is specular, and the reflection from the groove cut into the material is diffused. Therefore, the space between the groove acts as parallel sources of reflected light, like the slits in a transmission grating. Current technology can produce gratings that have very small slit spacings. Okay, grating are often labeled with the number of groove per unit length, which is the inverse of the slit spacing D. Here, slit spacing D. For example, if we have a typical grating rule with 5,000 groove per centimeter, it means that it has slit separation, the D, is equivalent to 1 over 5,000. Okay, so means that it's equivalent to 2.00 times 10 to the power of negative 4 centimeter. This is the meaning of the number of groove per centimeter. So in this figure, a section of diffraction grating is illustrated, okay, where we have a plane wave, okay, as the incoming wave projected or incident upon the diffraction grating, right, from left, normal to the plane of the grating. The pattern observed on the screen far to the right of the grating is the results of combined effect of interference and also diffraction. Each slits produce diffractions, and the diffracted beam going to interfere to each other and produce the final pattern projected on the screen. The wave from all slits are in phase as they leave the slits, right? For an arbitrary direction theta measured from the horizontal, however, the wave must travel different path of delta between rays, okay, from any two adjacent slits is equals to the d sine theta. If this path difference equals one wavelength, the order or the multiple integer of one wavelength, wave from all slits are in phase and a bright fringe is observed on the screen. Therefore, the condition for maxima in the interference pattern at the angle of theta bright is identically to this equation. D sine theta bright is equivalent to m lambda, where the m is equivalent to 0, plus minus 1, 2, 3, and so on. For the m equivalent to 0, we call it as 0th order maximum. This is first order maximum. If it is positive, it's upper part of the screen. Okay, if it is negative, it is lower part of the screen. In this figure, we can observe that the intensity versus sine theta, okay, for a diffraction grating from 0th order to the first, second, upper part of the screen or lower part of the screen is actually the same. In comparison to the single slit diffraction pattern, the intensity is the most on the central maximum. Okay, but for diffraction grating, the intensity is the same, distributed well. Let's take a look on conceptual example 37.4. A compact disc is a diffraction grating. Light reflected from the surface of a compact disc is multicolored as shown in the figure. The colors and their intensities depends on the orientation of the CD relative to the eye and relative to the light source. Explain how that works. The surface of a DVD or CD in this case has a spiral groove track, okay, with adjacent groove having a separation on the order of 1 micrometer. Therefore, the surface acts as a reflection grating. The light reflecting from the region between these closely spaced groove interferes constructively only in certain direction that depend on the wavelength and the direction of the incident light. Any section of the DVD or CD serves as a diffraction grating for white light, sending different colors in different directions. The different colors that we may see upon viewing one section change when the light source, the CD, or ourselves change in position. This change in position causes the angle of incident or the angle of the diffracted light to be altered. Right? Next one is conceptual example 37.5. Okay, the orders of a diffraction grating. Monochromatic light from a helium neon laser, lambda equivalent to 632.8 nanometer, is incident normally on a diffraction grating containing 6,000 groove per centimeter. Find the angles at which the first and second order maxima are observed. Right? So first thing we have to do is to figure out the separation distance. The D is equivalent to 1 over 6,000. Okay, which give us 1.667 times 10 to the power of negative 4 centimeter. Or this is 1667 nanometer. And we know that path difference is equivalent to d sine theta, okay, is equivalent to lambda m. Right. For the first order, sine theta 1 is equivalent to the m is 1 lambda over d. And our lambda is 632.8 over 1667. So from here, we will have theta 1 equivalent to 22.31 degree. For the second order, sin theta 2 is equivalent to 2 times lambda over d. So again, our final answer for theta 2, 49.41 degree. What if you look for the third order maximum? Would you find it? Right, so let's figure out whether the theta 3 exists or not. If it is exists, then we may find it. So sine theta 3 is equivalent to 3 times lambda over d. Okay, so as we know, maximum function of sine is 1. So since this is exceeding 1, it means that we cannot have the solution for sine theta 3. So it means that it does not exist. Application of diffraction grating. Okay, this is one of the application, which is diffraction grating spectrometer. The spectrometer is a useful tool in atomic spectroscopy, in which the light from an atom is analyzed to find the wavelength components. These wavelength components can be used to identify the atom. Right? So another application of diffraction grating is holography. Okay, where we are using diffraction grating to produce three-dimensional image of an object without screen. Okay, or simply known as hologram. In this hologram, right, a circuit board is shown from two different views. Okay, notice the difference in the appearance of the measuring tapes. Okay, and the view through the magnifying lens in A and B. So how the hologram is made? Okay, in this figure, light from laser source, okay, going to be transmitted into two paths. One of it directly, this light strikes the object and travel to the film. Okay, and the other one, this light travels through the film without striking the object. Okay, so, and finally they are going to combine and produce the image of the object. Our last subtopic, 37.6, polarization of light wave. In chapter 33, we describe the transverse nature of lights and all other electromagnetic wave. Polarization, discussed in this section, is firm evidence of this transverse nature. Okay, so any light wave consists of electric field, okay, represented by the orange color here, combined with the magnetic field represented by the green color here, propagating to the x direction in this figure with the speed of c, which is 3 times 10 to the power of 8 meter per second. This can be considered as schematic diagram of an electromagnetic wave propagating at velocity c, okay, in the direction of positive x. The electric field vibrates in the xy plane and the magnetic field vibrates in the xz plane. An ordinary light or beam consists of a large numbers of individual waves emitted by the atom of the light source. Okay, each atom produces a wave having some particular orientation of the electric field vector E. So you have lots of E. Each of the E correspond to the direction of atomic vibration of the light source. The direction of polarization of each individual wave is defined to be the direction in which the electric field is vibrating. For the individual wave shown in figure, okay, this direction happens to lie along the y-axis. Now, imagine all the individual waves that leave the light source in a beam of light directed along x-axis. Each individual electromagnetic wave will have E vector parallel to the YZ plane, but this vector could be at any possible angle with respect to the y-axis. Because all direction of vibration from a wave source are possible, the resultant electromagnetic wave is a superposition of waves vibrating in many different directions. the result is an unpolarized light beam like this figure. A beam of light is said to be linearly polarized if the resultant electric field E vibrates in the same direction at all time at the particular point as shown in this figure. Sometimes such a wave is described as plane polarized or simply polarized. The plane formed by E and the direction of propagation is called the plane of polarization of the wave. If the wave in figure here represent the resultant of all individual wave, the plane of polarization is the XY plane. This is the plane of the polarization, right? A linearly polarized beam can be obtained from an unpolarized beam by removing all wave from the beam except those whose electric field vectors oscillate in a single plane. We now discuss 4 processes for producing polarized light from unpolarized light. Okay, so the 4 types of polarization, okay, of light wave can be done via selective absorption or reflections or double refraction, or last one by scattering method. So the first one is polarization by selective absorption. So if you see here, this is the schematic diagram of the process for selective absorption. So here we have unpolarized light, okay, similar to the one that we discussed in detail just now, okay, where it consists or has lots of electric field E vectors in all directions that possible. And this unpolarized light is traveling, okay, along the red arrow here. This is a C, or the velocity of the lights. Okay, it's going to meet up a polarizer. Okay, this polarizer is made from some material whereby an alteration in the arrangement of the chain molecule within the material is made up, right? So the polarizer here, okay, going to polarize the incident light along its transmission axis. So we may set the transmission axis according what we want by altering the molecule chain of the material. So for example, in this diagram, we already select as this one as the transmission axis. Only E in this direction is allowed to pass the first polarizer here, right? So the rest of the E going to be absorbed by this polarizer. So now the polarized light going to be passed through the first polarizer having now E naught. Okay, we call this one as polarized light. Okay, and it's going to meet up another polarizer now named as analyzer. The analyzer allows the component of the lights parallel to its axis to pass through. So means that, okay, now from the first transmission axis, okay, this transmission, the second transmission axis, has theta angle, okay, to the respect of the first transmission axis. So means that the E naught that is allowed to pass through is the component that having E naught cos theta. only can pass through the analyzer. The component of E naught perpendicular to the analyzer is completely absorbed. Okay. The component of E naught, which is parallel to the analyzer axis, is transmitted through the analyzer, which is E naught cos theta. Because the intensity of the transmitted beam varies as the square of its magnitude, we conclude that the intensity of the polarized beam transmitted through the analyzer varies as I equivalent to I max cos square theta, where I max here is the intensity of the polarized beam incident on the analyzer. This expression is known as Malus law. Okay, applies to any two polarizing materials whose transmission axes are at an angle theta to each other. This expression shows that the intensity of the transmitted beam is maximum when the transmission axes are parallel, means that theta equivalent to 0 or 180 degree, and 0 means that complete absorption by the analyzer happen when the transmission axes are perpendicular to each other. This variation, okay, in transmitted intensity through a pair of polarizing sheet is illustrated by this figure. Because the average value of cos square theta is equivalent to half, the intensity of the initial unpolarized light is reduced by factor of 1/2 of as the light passes through a single ideal polarizer. So, from figure A to figure B and figure C is explained to us how much, okay, light can be transmitted through the polarizer. Okay, for figure A, transmitted light has maximum intensity when the transmission axes are aligned with each other. The transmitted light has lesser intensity when the transmission axes are at an angle of 45 degree with each other. Okay, and now the transmitted light intensity is a minimum when the transmission axes are perpendicular to each other. Almost none of the light going to be transmitted. Second method or type of polarization can be done via reflections. Okay, so this is a schematic diagram, okay, on how to do polarization by reflections. When an unpolarized light beam, let's say this is an incident beam, unpolarized, is reflected, incident you point second material from first medium to the second medium, okay, meeting the boundary, part of it going to be reflected and part of it going to be refracted into the second material. The polarization of the reflected light depends on the angle of the incidence. If the angle of the incident is 0, so means that it's projected, okay, directly normally to the second material, okay, the reflected beam is unpolarized. For other angle of incidence, the reflected light is polarized to some extent. And for one particular angle of incidence, the reflected light is completely polarized. It is found that the parallel component represented by the dot reflects more strongly than the other component represented by the arrow, resulting in a partially polarized reflected beam. Furthermore, the refracted beam is also partially polarized. Now, suppose the angle of incident theta 1 is varied until the angle between reflected and refracted beam here, the angle here, is 90 degree, as shown in this figure here, right? At this particular angle of incidence, the reflected beam is completely polarized, with its electric field vector parallel to the surface, and the refracted beam still only partially polarized. The angle of incidence here, okay, where this polarization process occurs is called as polarizing angle, or theta p. We can obtain an expression relating the polarizing angle to the index of refraction of the reflecting substance by using this figure. From this figure, we see that theta p plus 90 degree plus theta 2 must equivalent to 180 degree. Therefore, theta 2 is equivalent to 90 minus theta p. By using Snell's law of refractions, it gives us N2 sin theta 2 is equivalent to N1 sin theta 1. So in this case, we have N2 over N1 is equivalent to sin theta 1 over sin theta 2, where our theta 1 right now is polarizing angle, or theta p, over sin theta 2. And we know that sin theta 2 is equivalent to sin theta 2 itself is 90 minus theta p, which equivalent to cos theta p. So substituting this information into this equation, we will have N2 over N1 is equivalent to sin theta p over cos theta p, where sin over cos is actually tangent theta p, equivalent to N2 over N1. Therefore, theta p is equivalent to arctangent of N2 over N1. This expression is called as Brewster's law. And theta p here, sometimes also known as Brewster's angle. Sunglasses made of polarizing material reduce the glare of reflected light. Sunglasses made of polarizing material reduce the glare of the reflected light. So it is good for us to wear sunglasses during hot day or during raining while driving, because the unpolarized light scattered by the molecule of waters during rain will be blocked or polarized, okay, by the material of your sunglasses. Now, polarization by double refractions. Okay, so in solid, we can classify solid on the basis of the internal structure of it. Basically, we have two types of internal structure of the solid. We have two types of, whether we have crystalline or we have amorphous. What is the difference between these two types of the internal structure within solid? For crystalline, we do have some pattern of the arrangement properly or accordingly. For example, okay, this is chlorine and natrium, okay, arranged properly. But we have another type of the internal structure for solid, which is amorphous. For example, glass, okay, where the atoms or molecule within the glass is not arranged according or in a pattern like this. So it's distributed randomly. Okay. So what is the effect between these two different internal structure? When light passing through, okay, a solid, okay, where the solid has internal structure of crystalline, okay, the speed of the light, okay, is not the same throughout the material, okay, in all directions. The speed is different. The speed of lights that entering a crystalline material is different in all directions. But for the lights that passing through amorphous material, the speed of the light is the same in all directions. So due to this, in certain crystalline such as calcite and quartz, okay, the speed of light is not the same in all direction. Therefore, the light going to be polarized. Okay, and this kind of material has two indices of refractions. Hence, this type of material is often referred to as double refracting or birefringent materials. When unpolarized light enters a birefringent material, for example calcite, it may split into an ordinary ray, symbolized as O ray, and extraordinary ray, symbolized as E ray. These two rays have mutually perpendicular polarization and travel at different speed through the material. The two speeds correspond to two indices of the refraction for the material. NO for the ordinary ray, NE for the extraordinary ray, as represented by this. There is one direction, however, called optic axis, along which the ordinary and extraordinary rays have the same speed. If the light enters a birefringent material from an arbitrary direction, the different indices of refraction will cause the two polarized rays to split and travel in different direction as shown in figure just now. So table 37.1 here lists down for us the NO and NE and the ratio of it for different type of material. Right. So if we see this figure where we have a calcite crystal produces a double image because it is birefringent, or means that double refracting material. Okay. How is this happen? It's actually happen like this. Got that part. The last one, polarization by scattering. When light is incident on any material, the electron in the material can absorb and re-radiate part of the light. Such absorption and re-radiation of light by electrons in the gas molecules that make up air is what causes sunlight reaching an observer on the earth to be partially polarized. We can observe this effect called scattering by looking directly up at the sky through a pair of sunglasses whose lenses are made of polarizing material. Less light passes through at certain orientation of the lenses than at the others. This figure illustrates how sunlight becomes polarized when it is scattered. The phenomenon is similar to that creating completely polarized light upon reflection from a surface at Brewster's angle. An unpolarized beam of sunlight travelling in the horizontal direction parallel to the ground strikes a molecule of one of the gases that make up air, setting the electrons of the molecule into vibration. This vibrating charge acts like the vibrating charge in an antenna. The horizontal component of the electric field vector in the incident wave results in a horizontal component of the vibration of the charge, and the vertical component of the vector results in a vertical component of vibration. If the observer in figure here is looking in a direction perpendicular to the original direction of propagation of the lights, the vertical oscillation of the charge sends no radiation towards the observer. Therefore, the observer sees light that is completely polarized in the horizontal direction as indicated by the orange arrow. If the observer looks in other directions, the light is partially polarized in the horizontal direction. When we look up into the sky in a direction that is not toward the sun, we see the scattered light, which is predominantly violet. Okay, in our eyes, however, are not very sensitive to violet light. Light of the next color in the spectrum, blue, is scattered with less intensity than violet, but our eyes are far more sensitive to the blue light than violet light. Hence, we see a blue sky. If we look toward the west at sunset or toward the east at sunrise, we are looking in a direction towards the sun and are seeing light that has passed through a large distance of air. Most of the blue light has been scattered by the air between us and sun. The light that survived this trip through the air to us had much of its blue component scattered and is therefore heavily weighted towards the red end of the spectrum. As a result, we will see the red and orange color of the sunset or sunrise. That's all for this topic. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture video. Assalamualaikum.